Okay, today we're talking about one of the applications of quadratic function. And the application that we're focusing on today is projectile motion. When you take a baseball and toss it up in the air, that's one of the projectile motions. When you take a rocket and shoot it straight in the air, that is another projectile motion. Anything, an orange, that goes up in the air and comes back down, that is what we call a projectile motion. So what we want to model today is at what time, if you toss, in this case, an orange, at what time does it reach a maximum height? And also at what time will it actually land back on the ground? So let's take a look at a very simple example here, the tossing of a baseball. So a baseball is tossed in the air, and the height of the baseball is given by this model, okay, that function. And what we want to know is how far is the baseball off the ground at any given time from 0 to 4 seconds. So the first thing we're going to do is we're going to make a quadratic graph to actually model the height of the baseball. In order to do that, we're going to need to create a table, right? So go over here and then make a table over here. Call T for time and then H for the height. And the time is given to be the domain that we're working with for this particular problem is just from 0 to 4 seconds. So in order to figure out the height of the baseball at any given time, we're going to go ahead and plug the values into the function. So here is our function, which is our height function. And we're going to plug those values in there. So the first value is 0, so 0 goes in there. And if we did that correctly, then this is going to come out to be 0, okay? Let's do the same thing for when h equals to 1, when h equals to, when t equals to 2, and then once again when t equals to 3, and then once again when t equals to 4. So 1 second later, where is the baseball, right? 1 second later, where's the baseball? So let's see. The baseball is, I'm going to go ahead and plug 1 in here. And plug 1 in there and do my math here. So I have 4, take away 1, that would be 3. Plug 2 in, 2 as you can see. Plug 2 in there. And then that gives me 8. 8 take away 4 is 4. So this gives us 4 feet. And then similarly, I'm going to plug 3 in and then plug 4 in. Okay. So when I plug 3 in, then I get 12. And 12 take away 9 is 3. So this is 3. And then finally, I'm going to plug 4 in. This gives me 16. And 16 take away 16 is 0. So the ball actually hits the ground 4 seconds after it has launch. Okay? So these are our time. These are our time. And then the corresponding values are height. So let's go ahead and plot the graph to show the distance at any given time. We're going to need to go ahead and construct our x-axis and our y-axis here. Okay, please label the axes. This is your height. This is your time. And then the y-axis is going to be your height. Okay, and we're going to go ahead and label 1 second, 2 seconds, 3 seconds, and then finally 4 seconds after it has launched. This is going to be 1 foot off the ground, 2, 3, and then finally 4, and then 5. So plotting the dots, right? So the first dot that we're plotting is 0, 0, as you can see, right? 0, 0. All right, so 0, 0 is right here, okay? The second dot that we're plotting here is 1, 3, 1, 3, okay? The third dot that we're plotting here is 2, 4. So 2 and then 4. And then finally 3, 3, 3, 3. Okay? And then lastly 4, 0. 4, 0. Okay? And then if we connect, as you can see, if we connect, then the graph looks like this. Okay, so that's the graph, but it models the height of the function. And the way how we have to visualize this is that 1 second from the start, the baseball is now 3 feet from the ground. Okay, 2 seconds from the start, the baseball is now 4 feet from the ground, okay? 3 seconds, so now it has reached its apex and now it's coming back down, right? So 3 seconds has passed, the ball is actually now back to 3 feet from the ground, and so on and so forth. So that is the graph, and that's how we interpret the graph of a projectile motion. Now, the first question that we want to answer is, how long is the ball in the air? Well, the ball left the ground at time 0, and it doesn't really return to the ground until 4 seconds later. So clearly the ball is in the air for 4 seconds. So we say 4 seconds, okay? What is the greatest height that the ball reaches? So the greatest height is at the apex, right? The maximum point. And if you look carefully, clearly that is the maximum point. So what is the greatest height? Well, the greatest height is going to be 4 feet. Okay. How high is the ball 3 seconds later? How high is the ball 3 seconds later? Well, 3 seconds later, okay, 3 seconds later, let me pick a different color. So here's 3 seconds later, right? So 3 seconds later, clearly the ball is, we can kind of see clearly here that 3 seconds later, the ball is also 3 feet from the ground. So we go over here and we go 3 feet. Okay, after 3 seconds, the ball returns to just 3 feet from the ground. Do you think the ball is traveling faster from time 1 to 2 or from time 3 to 4? So these time spans basically are just 1 second apart, as you can see, right? These are just 1 second apart. But in terms of speed, in which time interval is the baseball traveling up faster? So what we want to do here to answer this question is we want to calculate the slope or the rate of change. So if you look carefully from 1 to 2, right? From 1 to 2, look, from 1 to 2, from 1 to 2, right? The rate of change from 1 to 2, the rate of change is 1 feet, okay? From 3 to 4, the rate of change is actually 3 feet. So it's actually going 3 feet per second versus 1 feet per second. So this, by looking visually, by looking at that, we can see that the ball, it's actually traveling faster. So we're gonna write the ball is faster from time 3 to 4 since its velocity is minus 3 feet per second versus 1 feet per second between time 1 and 2. All right, so there you go. Good job. Very nice. Okay, so a few things to remember when we're talking about projectile motion sort of problem. The letter T is always referred to time, and it represents the variable x. The letter H, in this case, that's the one we use, or sometimes we use the letter D for distance travel. That is represented by H is either height or distance, right? It represents the variable y, okay? And then one last thing to kind of keep in mind is when an object hits the ground. When an object hits the ground, that means the height of that object from the ground is 0, right? So when it hits the ground, that's hitting the x-axis, because the x-axis can act as the ground, right? So when it hits the ground, its height is 0, right? So when it hits the ground, basically, here's what we want to know. So usually when it hits the ground, its height is 0, okay? So by finding the x-intercept, by finding the solutions, you can tell when an object hits the ground, okay? And that's why finding a solution to equations, by solving equations, these are really important because it turns out it ties to applications that are really useful, okay? Great job, guys. I will see you guys in the next video.